Welcome to the NTI Sustainability Summit. In this session, we're going to be talking about how sustainability is a data issue and how better, more connected data will turbocharge a solutions ecosystem for greater impact. My name's Justin Taylor, and I am the AEC and Sustainability Solutions Product Manager at Autodesk, and I work in the Global Delivery and Solutions team. My background is in architectural design, design manufacturing, so prefabrication, DFMA. I also have postgrad in construction management, and I'm certified Green Star and BREEAM, so heavily focused on sustainability. Before we begin, I really like this statement. I think it really speaks out to what has to happen in the industry. We must make it easy to design and make sustainably. Okay, we need to make it as easy as it is to do unsustainably if people are going to start adopting and improving the way that our buildings and our infrastructure and our products are designed and made. As I said, sustainability is a data issue, okay? And we need to be able to create predictive simulations for optimal performance. We need to analyze and improve resilience, iterate designs to enable better energy and material choices. So creating real impact is based on connected, data-driven solutions. And hopefully this presentation will show you some examples of how we can achieve that. Let's take an infrastructure twin. A lot of people are familiar with tools from Autodesk such as InfraWorks or Forma. But how accurate, what can we get out of these tools that allow us to understand the environment? Okay, well, here we have a model of the Autodesk office in Toronto, Canada. And we can use the model generation tools to quickly bring in existing data to create a structure. But what is the accuracy of that? Well, what a lot of people don't know is that we can import additional data into these packages. So we went into the Toronto government website and we downloaded the latest LiDAR information freely available from government. We downloaded all the information around the mature trees around the city. We downloaded the government's data analysis, how many vehicles are traveling at different times in the day, what is the frequency, etc. So all of this data is freely available and you can get it from most governments. That data was brought into InfraWorks, and this short video shows how that data can be brought in and layered to build up a very, very accurate, very high fidelity replication of the city of Toronto. So here we can see the LiDAR data coming in, which is accurate to around 2 meters on a grid. We can see the road network coming in. Next, we have the trees. So these are the positions of the real mature trees around the city block around our office. And here comes the Revit model. So that's the design model. And the surrounding buildings are much more accurate than the standard ones InfraWorks can bring in. These were available, as I said, through the government website. So a super high fidelity model of the city. But what next? Well, in the same software inside of InfraWorks, we import that traffic data. And InfraWorks has a very powerful traffic analysis engine, okay? First of all, we can see the traffic and the traffic flow around the junctions at different times of the day based off the government data. And we can start to see how the traffic is backlogging and sitting still with idling going on. So we can see the efficiency of a network. We can go in and we can start to play around with the junction design, or we could simulate traffic lights and changing of the sequence to see if we can improve this information. But it is a very effective town planning tool in terms of logistics. The other thing that InfraWorks can do on top of this is it can export that traffic information. So out to Excel, we can export all the traffic data and the emissions. And here's an example where it's been brought into Power BI, so make it easier to digest. We can see the number of vehicles, the CO2, the NOx, and the particulates at any given point of the day, and the type of vehicles that are producing those emissions. So we understand how polluted the area is. And this is useful in existing scenarios or if we're building new layouts and new town planning, etc. Now we need to look at how we can mitigate this. So in this example, we bring the same traffic information into Forma. And to start with, we can then analyze the noise around the same junction around the Autodesk office. And you can see here that in the area in front of the office, just off of the road, we're getting up to the noise levels of around 110 decibels, which is pretty uncomfortable for people and wildlife. You know, if we want to start creating biodiversity in our cities and improving the overall health and well-being, we need to reduce noise and pollution. So one thing that we can do is we can look at terrainscaping. So Forma has a bidirectional link with Revit. And in Revit, I updated the terrain to create a very simple earth bank or BOM. I brought that back into Forma and reanalyzed it. And you can see immediately there's a drop of around 10 decibels just through doing this. And that's not including adding planting or further sculpting. So we can see the noise level has come down. We can also see that earthworks is altering the prevailing winds as it comes in, again, analyzed through Forma. But we can see it's starting to lift up the air faster and away from street level. So the pollutants are being brought up. So it's reducing wind speed and it's also lifting out the pollutants. So here we can actually see that our design is having a positive impact through the analysis. Finally, that information from InfraWorks, the InfraWorks model is exported and brought into Twinmotion. And this allows us to create, high definition animations and visuals of what this design would look like for planning reasons or community buy-in. It's also important to note that Twinmotion has libraries of indigenous plants for different regions. So these aren't just any trees or bushes that are dropped down. These are ones that would actually grow in that environment. And you can see how the overall site has a much greater aesthetic appeal. We're increasing biodiversity and we're reducing noise and pollution. Other things we can look at is what if we wanted, this was an existing building, but what if we wanted to invest in renewable energy? Well, again, Forma allows us to quickly analyze the overall site, the facades and the rooftops of the building, and understand the sunlight and the potential for photovoltaics. The model can be brought into Revit and greater analysis, more granular analysis can be done on different roof elements. So we can start to understand not only the PV energy production potential, but the payback time. So how many years is it going to take to pay back on a particular asset? Well, we want to look at the life cycle, as I said at the beginning, this connected data from start to end. So what about the creation of the solar panel in the first place? Well, here I've modeled up the solar panel in Autodesk Fusion, a design and make tool. And I've used all the materials that it would normally go to make up. So whether it's aluminium or steel or plastics or the silicon cells themselves, they've been modeled up. And I've connected the model to something called MakerSite. And MakerSite allows me to assess the embodied carbon of this design. So I understand what its footprint is as an object. And I can then create an environmental product declaration for this, maybe. Not only that, but it's telling me the overall material and manufacturing costs as well. So I can start to weigh up different design options, cost versus carbon. From Fusion, I can export this solar panel and I can bring it back into Revit. I can position this on the roof accurately and I can rotate it and angle it to its true inclination. And I can then assess the photovoltaic potential of just the solar panels and get a greater accuracy of the energy that I can produce. Towards the end, the operation and maintenance, the life cycle, that same model from Revit can be pushed into Autodesk Tandem. It can be connected up with operations and maintenance documents. It could be connected to EPDs, environmental product declarations. It could be connected up to monitors, sensors, and feedback panels. So at any given point, we can understand the energy that's being produced at any given time and whether a solar panel is working optimally or not, or if there is a problem. So we're creating a digital twin of that building. So let's look at the life cycle and let's start to understand how data needs or can be connected to improve this overall life cycle. We hear a lot of talk about material passports. They offer sustainable material selection, health and safety improvements, value preservation, regulatory compliance and certification. But how do they work in reality? Why are they relevant? Well, they're a mechanism which supports the circular design, as I mentioned. They allow us to rethink how we use materials and energy. We want to start reusing and creating this circular environment. They allow us to understand the products or materials in the building that can be continually reused in future projects, i.e. less waste, less use of virgin materials or brand new manufacturing. And as the world's resources become more limited, circular design is the foundation for the circular economy. We have no choice. This is a route we need to go down. So this diagram shows on the left a traditional process where we take from the ground, we make, and then it goes into landfill. At the end of the day, the building gets knocked down, it goes into landfill. With a circular economy, we start off with resources, we manufacture, we consume, and we use, and we try to recycle, downcycle as much as possible. So we're putting as little as possible back into landfill. And over on the right, there's an example from BAMB. This was a building that they produced in conjunction with iterate. It's a circular house where they borrowed all the materials from a different project, and it was returned after disassembly. So it's proving that it could be done. There's been quite a few examples of circularity and reuse of components or materials. And this is an early example from BZ. Okay, so Bennington Zero developed this housing development in Hackney in London. It was designed by Bill Dunstan and Partnerships in conjunction with LS Moore Consulting Engineers. They reclaimed 98 tons of steel for this development. They estimate it was 4% cheaper than using new steel, so there was a cost saving as well as the carbon. Okay. The cost of source and inspecting the steel, because again, you can't just take something that was structural and then reuse it. It has to be inspected to make sure it's right. They estimated that was around £1,000, making the reclamation itself cost neutral. 81,500 kilograms of CO2 was saved for the renewal of that, for the reuse of that steel, and 2,500 gigajoules of energy was saved. So quite significant just on this one development. Overall, 52% of the materials were required within their target radius in London. So they set out to understand what buildings were coming down, where they could get material to reuse it. And they set this target of the distance they would travel, because again, transportation incurs carbon costs through fuel, etc. So they set this target. Now, they did face issues. Okay, this was pre-material passports, pre-digital logbooks. Some of the issues they faced is that it required a team of people to source the materials. They had no way of knowing what buildings were coming down and where. So they had people calling around all the time. There was no centralized knowledge base, if you like. It required additional processes, such as inspecting the steel for any cracks or distortion, sandblasting, zinc treating it to make it rust-proof again. A different way of thinking around this is that the structural engineer carrying this out now holds the risk associated with the integrity of the steel. And clients are not always willing to accept reclaimed elements. Not all materials are easy to reclaim due to the way things have been constructed. So again, this ability to change our mindset in the way that buildings are put up. We need to design for disassembly. The use of adhesives, for example, makes it very difficult to separate materials and reuse them. So the use of nuts and bolts and screws is far better for recycling. Now, recently, Fletcher Priest Architects undertook a project, the Densia office in London. And as part of this development's unique approach to reducing whole life cycle carbon, they set out and developed a very robust platform for creating material passports on the project. And again, this presentation will be made available to you, and there is a read more link down here that takes you through to the full article about this. But at the end of the day, they created a platform for material passports that captures information. That information itself is wrapped up and encompassed inside something called a building digital logbook. So if you can imagine, it's like a supercharged digital twin of a building, and it contains all the material passports. And these material passports are linked to the elements, the individual components, or the materials inside of this building. Okay, so a digital logbook is an all-in-one information tool that's designed to encourage data transparency and availability, and allows us to understand what the building contains, where it is, and how to get to it and access it. It also, with the material passports, understands exactly what has happened to a component or building element throughout its life cycle. If we talk about something like an air conditioning unit, not only is it where did it come from, what is the manufacturer, what is its embodied carbon, what is its operating requirements in terms of energy, how often is it serviced, has it been serviced? So this entire history is wrapped up inside the material passport and then inside the digital logbook. Now, along with all of this data comes the problem of accessing only what you want and not being lost in a sea of data. And we need to look at ways to, if you like, construct and connect our data to make it readily accessible to those that need it. Here's an example of a hospital head wall where all the gas and the electricity and all the medical equipment is connected into. It's a complicated piece of prefabricated equipment. And it can be used by many different people, personas, so the patient, the medical staff, engineers, construction managers, mechanical engineers, etc. How do they only get the information they want about that component and not get lost in this sea of irrelevant stuff to them? Well, this is where two forms of classification come in. So first of all, we have taxonomy, which a lot of us are familiar with. So software such as Revit does this very well, pretty automatically. We create a new project, we call it a hospital, and we create zones, departments, and we create levels, and then we create rooms and we put equipment in those rooms. And Revit has the capability that the equipment already knows what room it's in, what floor level it's on, what department it's in, and what projects it's in. So the taxonomy is fairly straightforward, and it varies slightly depending on the particular persona that's accessing that data. But what we want to do if we move forward with digital logbooks and digital twins is we also need to look at ontology, which is the way that we capture rules and constraints. And this allows us to provide actionable insights. So the same head wall, imagine that it needs a power socket replaced. Okay. So the taxonomy tells us that the power socket is in the head wall. It's in a wall panel, in a room, on a ward, in a department, on a floor, and in the building. So it tells us how to get there. But in order to change that power socket, we need to understand that it's connected to electrical conduit with a wire in it. We need to understand all the information around that circuit. Where is that circuit connected back to? What switches or fuse boxes do I need to go to in order to isolate that circuit? Who else is it going to affect in the hospital, if anyone? Not only that, but if I'm working on that electrical conduit, I need to understand there is a gas pipe above it. Is there a risk that I could break that gas pipe? If so, I need to shut that gas pipe down. And again, where does that go back throughout the facility? What do I need to shut down? And the same thing with security console. So there are all these rules that are interconnected, and they need to be built into the digital twin. And here's just a quick final example of that kind of information coming into a digital twin. So this is tandem. And you can see here that over here, there is a valve mechanical unit, a valve that's been selected. It tells me all the information that's coming from Revit about its description, who it's installed by, the manufacturer, the model number. It shows me a link to the operations and maintenance manual, it shows me a link to the product data sheet, the EPD, the warranty documents. So I can go and filter and grab any information I need about that component very, very quickly. And the documentation will open up. But the digital twin can also act as a material bank. So there is a terminology called BAMs, buildings as material banks. So again, inside of Tandem, I can search for different types of material, and you can see the colorized image is showing me whether it's steel, whether it's concrete, whether it's brick, etc. So again, if my building had a date where it was going to be decommissioned, and I was putting up a new building, I could do a search and I could say, I'm looking for a certain type of steel. And the digital twin would come back saying, right, this building contains that type of steel, this is where it is. And it could have documentation that explains how I need to disassemble that building to get to that steel. And it would come along with all the material passports as well, if anything had happened or been altered during the lifetime of that building. Here's the final slide again, showing a prefabricated slab. And again, you can see here there is a link to the environmental product declaration, which then brings up a unique identifier and tells me everything about that slab. Again, what it is, what type it is, its dimensions, its fixing methods. So how can I take it apart? When it was manufactured, installed, the amount of steel inside of it. And it's controlled via a QR code. So from the manufacturer's site, up in the top right, you can see a photograph of those slabs. There's a QR code on there. We use the same QR code that is carried across onto the construction site, used by the contractors during the installation, and used at any point throughout building's life cycle, including disassembly, and if those can be used again. As I said, we need to design for disassembly. What goes up must come down, and it needs to stop going into landfill. We've got a number of ways of understanding how efficient a building is. And this is a simple Power BI mock-up of a project that I did with a client, where we created a capability that during the design process, and these are prefabricated wall panels, the designer could test out different material types, whether it's, you know, plyboard, whether it's fiberboard, the thickness of the sheet metal. And the dashboard fed back, providing the designer with the embodied carbon and also the overall circularity score. You know, how much recycled material is in there? Could it be recycled? Could it be downcycled and reused? So this provides the designer the ability to compare two different designs. And you can see actually that the design on the right has a higher embodied carbon score. And you might initially think, oh, we better go with the one on the left. However, the one on the right has a greater circularity score. So over its entire life cycle, it is a better option to go with in terms of sustainability. We can do things around transportation. So again, this is a Revit model of a house with prefabricated panels. And we want to understand how to get these panels from the factory to the site as efficiently as possible. So using things like Dynamo, we can create a script which we enter the size of the lorry and its capabilities for transporting bulk materials. So you can see we can go into here, we can set the width, the length, and the height of the container. It will look at the panels in the model and it will run an assessment and tell us how many lorries we need and what needs to go into each lorry in order that we sequence the build of the house properly. So again, using Revit and Dynamo, we can start to understand in much greater detail the logistics that are required and stop wasting or having trips with half loads or partial loads, etc. So there you can see the number of containers and what needs to go into each container in order. This slide shows that same prefabricated panel, and it's been designed in Fusion in this case, so that it can be easily assembled and easily disassembled. You know, each element, a study was carried out to understand, you know, how easy it is to take apart all of these individual components, reuse, reclaim, or recycle completely. So, you know, if a part is damaged, and it's made of steel, then obviously it could be melted down and reused. But if it's not damaged, it could go back in and be reused on a brand new panel. Also, the way that the panels are connected, they're slotted into steel connectors and then bolted. So again, there's no permanent fixture, there's no welding, there's no adhesives that are going to make it really difficult to start taking this building apart at the end of the day. In terms of renovation and retrofit, I think it's around 80% of existing office buildings require renovation and retrofit in order to meet energy requirements. It's a big task. How do you do that quickly? So for external studies, I'm a big fan of drones and photogrammetry. They are able to capture large areas super quickly. Very, very detailed. They produce site orthos, but they also generate three-dimensional point clouds and meshes. That information can come into tools such as Forma, such as Revit, and we can reverse engineer. LiDAR, laser scanning, is known by most people, and again, heavily used on internals where drones don't really currently go at the moment. So again, same building, an internal scan using laser scanning, you can see the quality of the images. That data, okay, can be brought into third-party products. So this is a third-party product called Point Fuse that integrates with the Autodesk Construction Cloud. And you can see the point cloud comes in. Now, point clouds are not the easiest things to work with inside of tools such as Revit. It's kind of hard to break them down and classify and understand exactly what's going on and off. And they're very, very heavy. So tools like Point Fuse allow us to create super lightweight, very accurate meshes automatically. And we can then classify those. We can say this part of the mesh is a floor, this part is a column, this part is a ceiling. That data can come into Revit. And here you see the mesh that's coming to Revit, and over on the right, we can see the hierarchy of those surfaces as they come in. Now, we can either model over the top and put real building elements in, walls, doors, windows, etc. Or if it's something that we don't need to model, modelers literally can get away with. If it's something that we don't need to model, it's not going to change, we can just add that surface into the Revit model, and it will be controlled along with the other Revit objects. So if we bring in a surface that's been classified as a ceiling, for example, it will switch on and off as we turn the other ceilings on and off in Revit. And this allows us to rapidly reverse engineer, scan to BIM, existing buildings and convert them into digital models that we can then produce digital twins of. It's just a few more examples. So thank you very much for your time. I hope that was of interest. Please reach out to us if you want any further information, and I hope you enjoy the rest of the sessions. Thank you.